Hey everyone, Mr. Skelton here. We are back at it. We are getting into lesson 2 in unit 9, and today we are going to be talking about probability again, but we're going to be talking specifically about independent and dependent events and what that means in terms of probability and how that affects probability. And so we'll jump right into it. Very easy learning target, pretty basic stuff here. We're going to see and be able to describe the difference between independent and dependent events. Okay. So down at the bottom here, we got some definitions with a couple of examples so you can kind of get a general understanding of what these two ideas are. Basically what we're doing is taking the probability of multiple events, so more than one event taking place. It's not like, okay, you roll a dice or a die, what's the chance you roll a 2? Well, that would be, there's 1 2 on the die out of 6, so you'd have a 1 in 6 chance of rolling the number 2. That would be your probability. We're going to be talking about multiple events that are kind of working together here, and we're going to talk about the difference between multiple events with independent and dependent. So we're going to start with dependent first. Dependent is when the outcome of one event affects the outcome of a second. So when the first thing happens, it affects the result of the second, and that's called dependent. So the second event depends on the first event. Okay, that's how you can kind of think of it for dependent. Here's an example. A raffle drawing where first, second, and third place prizes are selected at random from the same pool of people. So let's make an example. Let's say we have 50 people in this pool, and it's a raffle drawing, so first, second, third place. Well, let's go backwards. Let's go third place first. So the chances of you winning the third place prize would be 1 in 50. Okay, but as soon as you win, or someone wins that third place prize, they are no longer eligible for second place. So that means to win second place, there's a 1 in 49 because the person who won the third place prize is now removed from the pool. And then you have, I should put time signs there, but you have 1 in 48 for first place. Okay, so that is basically how you would give an example of dependent events, where these first events affect the rest. Okay, and we could multiply those together and figure out your percentages of winning first place, second place, or third place, and we'll get into that in a little bit, but just kind of describing how those things work. Second, independent events. Independent are when the outcomes of one event do not affect, that has no bearing on the second outcome. Those are called independent. Flipping a coin twice, right? If you flip a coin the first time, it has absolutely zero effect on the flipping of the coin the second time around. It's not going to affect it one way or another. Okay? So you got independent, you got dependent, and that's what we're going to focus on. Okay, so let's get into the first slide you have here at the top is just kind of a repeat of some examples of independent and dependent, and I just want you to pick which one is independent, which one is dependent. Okay? So go ahead and hit pause and see what you can do on your own. All right, number 1, a letter of the alphabet is selected at random. One of the remaining letters is selected at random. So the key word there is the remaining letters, because the first one is out, so what's left over is affected based on the first letter being removed. So this would be an example of dependent events. Number 2, the color of a car is selected at random. The type of transmission is selected at random. Those two things have nothing to do with one another. The color of the car has no correlation or no effect on the transmission, so that would be independent. Okay? Now, we're going to get into calculating some of these independent and dependent events, and we got a little bit of math lingo here, and I'll explain this to you once we get going. So basically, when you have independent events, this is kind of the equation you would use. The probability of A and B happening equals the probability of event A times the probability of event B. That's what you're going to do, is multiply the two separate independent events together. All right? So when we look at like this, what is the probability that a coin is flipped and lands heads up? So that would be 1/2. And then a face card is pulled from a deck of 52 cards. Those are obviously not related to each other. The coin has nothing to do with the 52 cards that are in the deck. Now, a face card would be a king, right? A queen and a jack. So there's 3 face cards, there's 4 suits. So you have 4 times 3, which is 12. So the chances of you pulling a face card would be 12 out of 52. And so what we'll do is just take our calculator out and we go multiply straight across. Really don't need a calculator yet, but we basically have 12 over 104, okay? So there's a 12 in 104 chance. Most people will turn this into, they'll reduce the fraction, so 12 fraction bar 104, just to simplify it a little bit. So 3 over 26. But then a lot of times we'll make that into a percentage. 3 divided by 26 is 0.115. So if you move that over 2 spots, 1, 2, that's 11.5%. There's 11.5% chance of this situation happening, where you flip a heads and pull out a face card on the first draw. 11.5%. Okay, that's the probability. Down at the bottom here, if a 4 is rolled with a single, if a 4 is rolled with a single 6-sided die, what is the probability of all 3 events? So we're talking about the first 2 events that happen here. This would be event 1, this would be event 2, and then we're adding this as the 3rd event. So again, these are all independent of each other. There's the heads, or the tails. Here's the face cards out of 52, and then rolling a 4 out of a 6-sided die. There's only a 4 on there, so again, we're multiplying straight across, so you get 12 over, let's see, 104 times 6 would be 624. So 12 divided by 624, and we have basically 0.019, so move it over 2 spots, you got a 1.9% chance of that happening. Again, this is an acceptable answer, as well as the percentage. Either one would work. If you want to reduce the fraction too, that also works. Percentages, most people can kind of make a connection with a percentage. It kind of makes more sense in their head in terms of the chances of that event happening. All right, so we're moving on. Now we're going to be calculating dependent events. So a little different here. Remember, dependent is where the first event affects the second event when it happens. So here is what you're going to be looking at here for dependent. And I'll kind of break down what this means. So this is for dependent events. Basically what this says is the probability of A happening times the probability of B happening such that A has already taken place. Okay, that's basically what that means. It's called conditional probability, the probability that B will occur given that A has already occurred. That's what this means right there. That vertical line in between B and A is the probability that B will happen given that A has already occurred. All right? So that is what we're going to focus on the bottom examples. So what's the probability of 2 aces being drawn consecutively from a deck of 52 cards? Well, there's 4 aces total, right? So we're starting there. On the very first pull, there's 4 aces, there's 52 cards, so the probability would be 4 out of 52. On that second pull, drawn consecutively, if you pulled the first ace out, there would now only be 3 aces available to you out of 51 cards, right? Because you pulled the ace out, so the ace would be subtracted from the 4, and obviously that 1 ace card would be subtracted from the 52. And just like before, we multiply straight across, so we're going to get 12 over 52 times 51, and I get 2,652, and I take 12 and divide it by 2,652, hit equals, and I get 0.0045. If I move that over 2 spots, 1, 2, I basically have 0.45% chance. So that's a very small chance, okay, of that happening, pulling 2 consecutive aces, 0.5% chance. This is the decimal answer, this is the percentage answer. Right underneath it, it says, oh, one thing I forgot to mention to you, you don't have to do this, but you'll see this a lot. So for this situation, you would write it like this: the probability of event A and event B taking place would equal the probability of A drawing the first ace, okay, times the probability of the second ace knowing that A already took place. That is how we would write that out, okay? So on this one it says, what is the probability of the third card also being an ace? So I'm going to write out the form. We don't have to do it. What I'm writing in blue, you don't have to do on your homework or test or anything. I'm just kind of showing you the algebraic form of this. So the probability of event A, B, and C happening, which is first ace, second ace, third ace, would equal the probability of event A, pulling the first ace, times the probability of B happening, knowing that A already occurred, times the probability of C happening, knowing that event A and B occurred. That's how kind of you would write that out. If you want to think substitution, it would look something like this. You would substitute the 4 out of 52 because that's the first event. The second event would be 3 out of 51, and there'd be 2 aces left to pull out of 50. And we would multiply those together. So 4 times 3 is 12. That would be 24 over, it's going to be a big number here, 52 times 51 times 50. And we get 132,600. 24 divided by second answer equals 0.00018. So 1, 2, so 0.018% chance of that happening. So this would be your decimal answer in blue that I just circled, and this would be the percent chance of that happening. Very, very small. All right, that's calculating dependent events. On the very back, got a couple more examples here for you. Very, very similar. Now, I'm not telling you which one is which. One could be independent, one could be dependent. Want to see what you can do? Try it, and then hit play to check your answers. All right, so the first thing I always do when I'm doing these examples is to figure out, is it independent or dependent? What is the probability of drawing 3 cards at random, which are all aces, if each card is replaced between each drawing? That's going to be independent, right? The cards are replaced. So 3 straight aces would be 4 out of 52. The card's replaced, so it's still 4 out of 52. The card is replaced again, 4 out of 52. You're always drawing out of a pool of 52 cards. There's always going to be 4 aces, because it's even if you pull the first ace and you replace it, there's 4 back in there. Okay? And again, if you were to write this out algebraically speaking, I'll do this in red. The probability of event A and B and C happening would just be the probability of A times the probability of B times the probability of C. There's no dependent aspect to this, okay? We could multiply those together just to save some time. You guys know how to multiply those fractions, top times top, bottom times bottom. Bottom one, what is the probability of drawing 3 cards at random, which are all aces, if the cards are not replaced? So that is dependent, and this is very similar to what we just did. So this would be 4 out of 52. When you pull that first card out, though, it is not replaced, so 3 out of 51, and then 2 out of 50. And again, you could multiply those fractions out and get your percentage, okay? So hopefully this you catch on to this pretty quickly. Sometimes it can be a little confusing, but hopefully you're understanding the difference between independent and dependent events and how to calculate their probability. I'll see you in class. If you have questions, as always, looking forward to working with you. Take care.